Hi, and welcome to video 2.2 in our series on building a simple electronic structure program in MATLAB. In this video, we're going to show how to implement a set of Gaussian basis functions into our computer program. And so this is the one where if you have very little programming experience, we're going to walk through every step of the way on this one and sort of outline exactly how we're going to convert information from the idea of these functions into what we need to put onto a computer so that we can access it and do all the things we need to do with it. So hopefully this should be pretty easy to follow. What we're going to be doing is we're going to be programming our Gaussian functions into our computer set. And so if we think about a Gaussian function or Gaussian basis set, we need to know what information do we actually need to store for each basis function or each orbital. Each Gaussian function, we're going to only for each basis set, we're only going to consider s orbitals in this version of the program. And so for each individual orbital, we really only need 5 pieces of information. We need to know the amplitude of our Gaussian function, our exponent, which we're going to call alpha, its x, y, and z location. So if this is three-dimensional Gaussian x, y, and z, it takes this form. So we have x naught, y naught, z naught. And that's it, those 5 numbers, our normalization, our exponent, and our location. And it turns out that if we stop and think for a second, this a value is capital A, our normalization constant, is not independent. It only depends on alpha. You really only need 4 numbers. And so just take a second and just see if you can figure that out for yourself. Feel free to pause the video. Okay, have you gotten your number for the normalization constant? You should have gotten 2 alpha over pi to the 3/4 power. And so what we're going to do is we need to first write a program that can build these individual Gaussian functions. And then we're going to write a second program that's going to build our basis functions. If you remember from the previous video, our basis functions are going to be sums of Gaussians with different exponent values or different contraction coefficients. And so what we're going to do is we're going to make one cellular array, which we're going to call basis. We're going to use this throughout the whole program. And basis is going to have n elements, and each element in basis will be a single basis function, which will be a structure that contains different Gaussians in it. And we'll see how we put that all together in one nice compact spot. This is not by any stretch the fastest way to program this. It is, however, a very easy and convenient way to program it so that you can see the underlying physics going on rather than getting in the way of, am I writing this program so that it executes as fast as possible? That's not really the point of this exercise. Okay. So then finally, once we have know how to write an s orbital in the computer, then we need to be able to build our basis functions. Our basis functions should depend only on 2 sets of numbers. First, the list of atomic numbers, or which nuclei we're including. We're going to call that list z of n, for z for atomic number. And then we also need a 3-tuple set of atomic coordinates. So AL is going to be an n by 3 array, where the first column is going to be the x component of each atom, the second column is going to be the y component, and the third column is going to be the z component. And then for each type of atom, we're going to need to get the appropriate combination of Gaussians to make up our basis functions. We're just going to get this from the literature. And so for each Gaussian basis function, we're going to use our function build s orbital to build that individual Gaussian basis function. I got the numbers for hydrogen, which is what we're going to be dealing with first, from the basis set exchange. If you go and look at the basis set exchange for 6-31G, which is a common, not great basis set, it's just simple, you'll get a couple different numbers. The first column here are your list of contraction coefficients, your alphas. And your second set of numbers is your basically your population. So how much of each normalized Gaussian is your basis set composed of. And then we have 2 basis functions for each hydrogen atom. Both s orbitals, one that has 3 Gaussians and one that has a single Gaussian. So for every hydrogen atom we add into our we use in our program. We're going to have two basis functions. There's a little bit of a confusion here. Basis at exchange says that these numbers come from this paper. I went and read this paper. I couldn't find this number anywhere in there. This paper is all about second row element, so it's a little bit misleading, and I apologize for that. But these are at least consistent with also what the program Gaussian uses. Okay, that little caveat out of the way, let's hop over to MATLAB and start the work of actually writing these up. This is the HF driver program that we built last time, and now let's go ahead and start implementing this. The first thing we want is we need to build a single Gaussian function, so we're going to edit, build, S orbital. Write that file. All right, so we're going to make this a function, and a function in MATLAB is going to return a set of values. And so we're going to say orbital. It's going to return orbital equals build S orbital. And we're going to need to give this 4 different things: an X location, an atom's Y location, an atom's Z location, and an exponent alpha. Okay, and I said that each primitive Gaussian is going to be a structure, and the way that we make a structure in MATLAB is we use the dot operator. And so I'm going to say temp.x0 equals ax, temp.y0 equals ay, temp.z0 equals az. I'm going to put these semicolons in here. They're going to prevent output from coming out. Temp.alpha equal alpha. And then temp.n, the normalization constant, 2 times alpha divided by pi to the 3/4 power. And then orbital equal temp. All right, so I'm going to save this, and then we're going to show how that actually makes an S orbital. Say F equals build S orbital. Let's have it be at 0, 0, minus 1, and an exponent of 7. Okay. And you see how it returns an orbital with an x0, y0, z0 component, an exponent alpha, and a normalization constant n. If I write f.alpha, I will access the number 7. Or f.x0, I should get 0, f.n. Right? So you can see how I can use the dot operator to access individual pieces of my orbital. So now that we know how to build an orbital, we need to go ahead and build our basis functions. Edit, build, basis. Let's create that file. Again, we're going to make a function. This time it's going to return 2 things. It's going to return the total number of electrons in our cell array of basis functions. So to return 2 things, we're going to use brackets, basis, comma, n, equal build, basis. We're going to put our input arguments, which are going to be the list of atomic nuclei and atomic coordinates. Okay. All right, so the first thing we need to know is how many atoms we have. N atoms equal size of Z2. It's just the size of Z. N equals 0. That's going to be the total number of electrons. Total number of basis functions is going to start out at 0. And now what we're going to do is we're going to loop through each atom. So we're going to make a for loop for index equal 1 through n atoms. x0 equal al index 1. Right, so we're going to get the x component for each one, the y component, and the z component. And now we need to, now that we have the atomic locations for each orbital, for each atom, now we need to get the right set of exponents. And so we're going to use something called a switch case. Switch Z index. Case 1. So it's basically we're saying we're going to take the number that's contained in Z of index, so Z1 and then Z2 and Z3 as this for loop progresses. And we're going to do different things for different values. So case 1 if Z index equals 1, that's hydrogen atom, right? Z atomic number 1. N equals N plus 1, so we add 1 electron. And now we add 2 basis functions. We're going to get these numbers, 18.73, 11370. We're going to get these numbers directly from the website, 0.0334946. And there are a couple of different ways you can get these numbers. You can get these numbers by fitting several Gaussians to a Slater orbital. For one Slater orbital, you could get them by minimizing the energy of the atoms, 2.8253937 with respect to the exponents and coefficients, 0.2347269. This is really boring to watch, and I apologize for that. 0.64012117, 0.8137, 813,75733. Okay. Alright, so now we have those exponents. NB equal NB plus 1. We're going to have one basis function. Basis of NB. So we're going to access the cell array NB, which currently does not exist, and we're going to define a few things. First, we're going to find that it has 3 Gaussian functions in it, so dot n equals 3. Basis NB dot C equal S. So the coefficients here are just these 3 values, the second column vector of our matrix S. And then basis NB dot G. So we're going to have an array of Gaussian structures here. So the first one is build S orbital X naught, Y naught, X naught, Y naught, Z naught, S 1, 1. Basis NB dot G 2. Same thing, just with the second contraction or second exponent, 2, 1, and basis NB dot G3 equal build S orbital space or orbital X naught, Y naught, Z naught, S 3, 1. Okay, so we've added those. And now we can add the next basis function, right? We're doing 2 basis functions for each hydrogen atom. That completely defines our basis function, our first Gaussian. So let's do NB equal NB plus 1. All right, the second one only has 1 Gaussian in it. Basis NB dot C equals 1. Basis NB dot G build S orbital X naught, Y naught, Z naught, and then you just have to look up this number 0.1612778. Okay. Right, and so we've added 2 basis functions for the hydrogen atom. Case 2. Helium atom, right? So that would be the helium atom. So you can go to the basis set exchange yourself and see what the orbital for a helium atom would be. I'm going to leave that as an exercise to you, so you don't have to watch me keep typing here. End, and that should be it. So if we now have our function, let's see here, basis N equal build basis Z comma AL. Should get 4 out. So what I did there was Z is 2 hydrogen atoms. In AL, they're located 3 angstroms apart. And so if I were to do Z equals 1 and AL equals 1, 0, 0, minus 1, 0, 0, 3, I should get 6 basis functions out. Build basis. And there we go, where B3 dot should, okay, right? And so we can access each element of our cell array. And so now we know how to make our basis functions on the computer and store all of the information we need in sort of a compact place where we know how to access it programmatically. In the next video, we'll start trying to figure out how to evaluate different matrix elements. We'll look at the overlap matrix and the kinetic energy matrix and see how we can build those matrices starting from these Gaussian basis functions. I hope you'll stay tuned. Bye.